Fuzzy matching is overkill when only the diacritic changed. PostgreSQL unaccent removes that mismatch before full-text ranking, preserving fast index search. You'll see how to connect the pieces into a workflow that indexes text and finds accent-insensitive matches. I'm Professor Pi, teaching search and IR with simple Python. Accents cause a lot of real search friction. People type plain ASCII and miss results stored with accents. Engineers often reach for fuzzy matching, but that slows queries and muddles ranking. Using PostgreSQL's unaccent before creating the tsvector keeps matches exact, fast, and rankable. This approach is particularly practical for titles and short bodies when you want predictable relevance for interactive queries. We want the same normalization steps on documents and on queries, so the index and the parser agree. If the index strips accents, but the query parser does not, you lose recall. If both strip accents, you keep fast GIN indexes and reliable TS rank ordering. The goal here is a compact pipeline. Ingest text, normalize accents, index the result, and run the same query spelled two ways to confirm rankings match. We will build a tiny project that links a Python client to PostgreSQL, creates an accent-aware text search configuration, indexes 3 small documents with accented and unaccented variants, adds a GIN index, and runs the same search twice to show equivalent rankings. The code is intentionally small, so you can see exactly where normalization must happen and avoid subtle mismatches. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We need to first verify the database connection path is clean and testable before touching search objects. This snippet opens a psycopg connection and verifies PostgreSQL answers a minimal query. It uses psycopg.connect to create the shared con object that later snippets reuse, and then runs con.execute with a tiny select one to exercise the exact client path your application will use. The reason is practical. Accent-insensitive search can fail for boring reasons, like connecting to the wrong database or a permissions mismatch. So this check confirms the session is reachable before creating unaccent dictionaries, configurations, tables, or indexes. The visible output simply shows the PostgreSQL session responded, which matters when you later debug relevance behavior. With a live connection, we must teach PostgreSQL how to remove accents before stemming, so both indexing and querying share the same steps. This example creates a text search configuration that normalizes accents before stemming. The snippet installs the unaccent extension, copies the built-in English configuration into a new app.en configuration, and then alters the mapping so unaccent runs before English stem for word lexemes. The code calls con.execute to apply each step and runs tsvector on a test string like Café's resume, so you can see the lexemes that will be stored. That small check shows the unaccent plus stem chain working in the parser, which prevents a common failure where index and query use different normalization paths. The visible output lists the normalized lexemes PostgreSQL will use. Next, we need to put some data into the table and ensure the tsvector column is populated using that new configuration. This code loads a tiny corpus where accents appear in titles and bodies, and stores a prepared search TSV using app.en. The snippet creates a docs table, and then uses con.execute many to insert 3 readable rows, deliberately including both accented and unaccented spellings so we can test recall. The insertion logic runs the app.en configuration when generating search TSV, so the vector stored in the row matches the query parser we built earlier. In production, you want the vector update close to your write path, so updates and inserts never diverge from parsing rules. The visible output confirms the corpus size that later ranked queries will search. A packed index is what keeps these searches fast as the table grows, so we add a gin index on the tsvector column next. This example adds a gin index on the prepared search TSV, so queries use an index scan instead of table scans at scale. The snippet runs con.execute to create an index named docs search gin directly on search TSV, which is the same normalized tsvector produced by app-n. Without that index, a demo still works, but real catalogs quickly slow down. The snippet also queries PG indexes as a compact sanity check to show the index registration instead of doing a full planner inspect. The visible output shows the index name PostgreSQL registered, which matters before you rely on the path in production query code. Now we can run the search itself twice, using both ASCII and accented user inputs to compare results. This snippet runs the final PostgreSQL search twice, once with plain ASCII input and once with accented input, and confirms they rank results equivalently. The code uses web search to tsquery with the app-en configuration, so query parsing follows the same unaccent and stem chain as indexing. It uses con.execute to bind the user query as a parameter and selects tsrank as a relevance score for ordering. The key check prints ordered IDs for both spellings to confirm that matching and ranking are equivalent, not just that something was returned. The visible output shows the equivalent ranking and the top matched row, which is the baseline behavior promised at the start. This tiny demo maps directly to real systems. Replace the 3 rows with your product catalog or article titles. Keep the same app-n configuration, and ensure writes always update search TSV. The same pattern reduces missed hits from accent mismatches without adding expensive fuzzy checks or extra ranking complexity. In short, run unaccent before stemming inside the same search config, and your index and queries will agree. Use this when users mix accented and unaccented queries and you need fast, ranked results. One caveat: unaccent removes diacritics globally, which can collapse distinct words in some languages, so validate on your data. A practical next step is to weight the title higher than the body, and then tune tsrank normalization so title matches bubble to the top on short queries. Apply set weight when building search TSV for the title field, and experiment with tsrank normalization to see how top results change on your real dataset, like your product feed or content catalog. If practical search tips help, subscribe and watch the other IR videos.